Hi, this is Stephen Brower from Mountain Valley Community College. This is for CSIT 256 Computer Architecture and Assembly Language. And this is to accompany Stallings Chapter 4, which is looking at cache. And what we'll do is first we'll give an overview of cache, then give an overview of the three different mapping algorithms, and then we'll have a specific example, so a particular computer, and we'll trace through the different algorithms for it. So just as a reminder, the cache is a copy of portions of memory. So not all of memory can fit simultaneously into the cache, just portions of it do. So what the CPU will do when looking for memory, it'll take a peek, is it in the cache? It'll peek first to see if it's here. If it is, it pulls the word, which usually is the byte, that it needs out of that piece of the cache. If it's not in the cache, then that block of memory would have to get brought onto the cache. And as we'll see later in Chapter 5, the static RAM is a different memory type than the dynamic RAM, which is our primary memory, and it's expensive, which we'll see, and that's why there's a smaller set. What's logically shown here is that the collection of data that's in the cache is a line. So it's just logically we have a line, so there's multiple lines within the cache. The number of bytes that are on the line, that's a block of memory. So one other thing we look at in terms of memory, it's that it's multiple blocks where each block will fit into a line in the cache. Depending on which line it is going to depend on the mapping algorithm that we use. Whoops. Okay. So in direct mapping, is that blocks will map to only one line. And so what the CPU will do, if it's looking for memory, it'll look at a specific line in the cache to see if it finds it. Since multiple blocks can map to the same line, the tag needs to be loaded on the line at the same time to distinguish it. So if the CPU is looking for a particular block and it looks at this line and it's not there, then that block is brought onto the CPU. Suppose it's looking now for a different block, but that other block also maps to the same line. Okay, maps to the same line. It'll have to compare the tag. Well, if that's not the same as the one it's looking for, then that block will have to be brought onto that line into the cache. So that's the direct mapping. In associative mapping, blocks can map to any line in the cache. So blocks map to any line. So when the CPU is looking for a block, it has to scan all the lines. So let's say the CPU is looking for a block. Okay, the CPU is looking for it. Oh, sorry. It'll scan the entire cache looking for the block. And if it doesn't find it, then it'll bring it in. Now suppose it's looking for another block. It'll scan the entire cache looking for the other block, and then that'll be brought into the next free line in the cache. What does happen at some point later is if there's no free line in the cache, one of the blocks has to get removed. And so one of the things that is referenced is there's a different algorithm that's used for determining the victim block, which is the one to actually be removed. So the downside of the associative is it has to do the scan of the complete cache. So set associative mapping, and it's referred to K-way. K is the number of lines that are in the set. It logically breaks the cache down into sets. And then each set will have multiple lines. And so K lines is how many it will have. So a two-way set associative mapping, there would be two lines in a set. So when the CPU is looking for a block, it only has to scan the lines that are in the set to see if the tags match. So if the CPU is looking for a block, it'll look at the set to see those couple of lines that are there. Does the tag exist it's looking for? And if not, it'll be brought in. So suppose it's looking for another block that also maps to the same set. My animation got a little carried away here. It's really only scanning the first set, but it didn't find it. And so that block is brought in. And so this way we actually can have two blocks simultaneously in the same set that are sitting in different lines of the set. When the CPU is doing its search, it only has to look at a smaller number of lines. It can eliminate the thrashing that we identified in direct, and it can eliminate the scan of the entire cache that we had with Associative. Okay, so now what we're going to look at here, and again, there's a Word document. I'm saying again, that's because I did have a dry run before this. There's a Word document in Canvas that goes through a specific example, and the specific example, it's the same memory and the same cache, and then it looks at the three different algorithms that are there. So this first slide here, I want to just do an overview for on the hardware. And a couple things that will help us with the calculations later. A K is 1024. So 1K bytes is 1024 bytes. 1024 is 2 to the 10. A megabyte is 1024K. That means it's 1024 1024s. So 2 to the 10 times 2 to the 10. When you multiply like numbers together with the exponents, you add the exponents, that's 2 to the 20. Now, in this particular example we're going to be looking at, it did say the line size is 32 bits, and that is 4 bytes. So there's 1, 2, 3, 4 bytes that would go onto a line. To distinguish which word we're looking for, we would need 2 bits. So, for example, 00, 01, 10, 11. So 2 bits are needed. So for all three examples we're going to look at, the direct, associative, and set associative, the word size is the same. The memory that we're going to have for this example is 16 megs of RAM. 16 is 2 to the 4. Meg, remember, is 2 to the 20. So we're going to have a total of 2 to 24. Since this is byte addressable memory, then that means each byte can be addressed, which means we need 24 bits for the memory address. So the total memory address that we're going to be referencing is going to be 24 bits. Of the memory address, 2 of those bits are going to be for the word. And by the way, in terms of the number of lines, so for this example, the 16K is the number of lines. So 2 to the 4 times 2 to the 10 is 2 to the 14. That's the number of lines. That's as opposed to being the size. So if there's 2 to the 14 lines and we have 4 bytes on a line, then what we end up having is 64K is the size of the cache. Okay. The total number of blocks. So since a grouping of bytes maps to a line, the line size has will basically use to determine the number of blocks we have. So if the total memory we have is our 2 to the 24, and the line size is 2 to the 2, so then 2 to the 22 is the number of blocks that we have in terms of memory. Okay, now we'll go on to direct. So remember, in direct mapping is that a block will map to a specific line. So part of the memory address is going to say what line should be looked at. Well, the lines we had figured out there were 2 to the 14 lines, therefore 14 bits is needed to distinguish the line. Now, multiple blocks can map to the same line, and so we need to then figure out the tag to distinguish one block that's on the line from another. Well, there's 2 ways we can do it. Well, we can back into it. The backing into it, we have 24 bits minus 14 minus 2, and we end up with 8 bits. So in other words, we can back into the tag. The other way is to think of it logically. If we have a total number of blocks of 2 to the 22, and the number of lines we have is 2 to the 14, then 2 to the 22 divided by 2 to the 14, so the number of blocks divided by the number of lines is going to give us, then these are the number of blocks that will map to the same line, so we need 8 bits to then distinguish them. So with direct mapping, which means if we're doing a memory address, if we're referring to memory, a portion of that is going to be what line to look at, a portion of that is going to be the tag, a portion of that is going to be the word. Okay, so what we're now going to do is look at, it's the same hardware, but we're going to look at a different mapping. And in associative, the block can map to any line. Well, we have 2 to the 22 blocks that can be on any line. Well, that means we need to uniquely identify the blocks. Well, it would take 22 bits to represent each individual block. So an associative mapping of the 24-bit address, 2 would be used for the word, 22 would be used for the tag. And remember, it's scanning the entire cache. So in this case, there's going to be 2 to the 14 lines of cache that it's going to be comparing 22 bits to see if they're the same. Okay, so now K-way set associative, where our K is 2. And what that means, and my animation or my skills are not the best in the world, but this is showing 2 lines are in a set, 2 lines are in a set, 2 lines are in a set. That's what I'm trying to show here. And so that means that when the CPU is looking, the first thing it has to determine is which set to look at. Well, the sets are, since we're going to have 2 lines in a set, and we have 2 to the 14 lines, then that would mean 2 to the 14 divided by, which are K, in this case K, the little k, is 2. That's the number of lines that are in the set. So 2 to the 13 sets, so 13 bits are needed for the set. Excuse me. So now, since multiple blocks map to the same set, we need to distinguish which block is there by looking at the tag. Well, just like we did with direct, there's 2 ways to get there. One, we can back in. So the 24 minus the 13 minus the 2 is 9, and that would be the 9 bits. So that's one way to get there, is to back into it. The other way is to think of, well, we have the total number of blocks, so total number of blocks is 2 to the 22. Total sets we have is 2 to the 13. So 2 to the 22 divided by 2 to the 13 is 2 to the 9. Therefore, 9 bits is needed for the tag. So the total, if we look at the formulas that the book has, there's about a dozen formulas for each of the different mappings. I didn't use all the formulas. And as you saw with the last thing with the tag on both direct and in K-way set associative, we could back into the tag 2 different ways. So don't feel obligated when you're later working in the architecture lab, don't feel obligated that you have to use every single formula that you see and then solve it. You don't need all the formulas. So it's like a set of simultaneous equations, but we have more equations than we really need to solve the problem. Okay, again, so this was going through mapping algorithms for cache. And the last thing we just went through here was for a piece of hardware. So for a set of memory and for size cache, we went to see how the mappings would be different. It's byte addressable memory. So that means when we're looking for a memory block, we're looking for 24 bits to identify that particular memory, that byte of memory. We're looking for a byte of memory. There's 24 bits to identify it. And so what the CPU will do is, in terms of where to look in the cache, it's a portion of the address will say where to look. So in direct mapping, it will look at a portion of it to figure out what line to look at. In K-way set associative mapping, it'll look at a portion of it to say what set to look at. And in associative, it's just going to look at 22. It's going to look at most of the bits to scan the cache looking for the tag. Okay, that was fun.